Alright then, let's compare the results from the skip sampling with those from the OLS. Okay, where is the OLS? Okay, so we have the OLS function right here. So then this is OLS. Okay, OLS. Okay, right. So then we have the dependent variable, independent variables, and this one indicates the display of the output, right? Okay, let me run this code. Okay, here we go, right? Yeah, okay. Just to make sure here, let me say the TISP. This is from Bayesian. Oops, I don't need this figure as estimation results. Alright. Okay. Let me put some space. Then let me run this again. Alright. Okay. You see that this value and this value are quite close, and this one and this one are quite close, and also this one and this one. Beta 3 estimates are very close between Bayesian estimation and this OLS. Okay, and sigma 2 square is almost 2.06, 2.5, right? Okay, looks good, right? So then you know that these OLS estimates utilize what? Only the data. And what about Bayesian estimation? This use both the information in the data and prior. But in this case, the outputs are very close. Why? Why? Because in this experiment, we didn't specify a strong prior, right? Here, prior for beta is what? It's normal distribution. Its mean is 0. Okay, zero mean is quite different from what? True values. True values are what? True values are 1, 2, and 3. But my prior mean is 0, right? This is quite different. But the variance is 9, which means standard error is 3. And 2 standard error is what? 6. That means I think roughly beta could be around 0, but my prior information is not that much, or my prior is not that strong, because the I guess the standard error is again 6. So I means that it's roughly 0, but it could be -6 or +6. It must be between -6 and +0, +6, right? So then it could be any value between -6 and 6, right? So then my prior is not that tight, or I would say my prior is not that strong. And same for the prior for sigma square here, right? But what if I have very strong prior? Which means what? Which means what? Which means what? So the still my prior mean is 0, and then my variance, my prior variance is very small. I would say 0.01. Okay, variance is 0.01, so that means standard error is just 0.1, right? So then 2 standard error is 0.2. So then I guess the beta must be between minus 0.2 and plus 0.2. Right. So then I believe that beta must be very close to 0. Okay. Yeah. Okay. And let me run this. Oh. Still is 1, 2, 3. It's still close to true values, right? Because still the data is very informative. So that means my prior is not that strong. It's not beaten by the information in the data. Let me try the stronger prior. 001. Yeah, you see that now the Bayesian estimates are very close to 0. And then if I put the stronger prior here, then what happens? Yes, it's almost 0, right? 0, right? 0, right? Okay. And if my prior is not that strong, again, okay, so then let's say 0.009. Yeah, it may look strong, but the data is so informative. We have very accurate estimates, right? So then let me put one more 0 here. Yeah. Okay. So now this 0.6, 1.6, okay, 1.9. So then these three values are quite different from the oldest estimates. And true values are again 1, 2, and 3. But these values are quite different, right? So then these Bayesian estimates are between what? Between OLS estimates and what? My prior means, right? So these Bayesian estimates are the weighted average between what? OLS estimates and my prior means, right? And then the weights are determined by what? Determined by the variance here, variance of OLS estimates, and then my prior variance. So that if I have the smaller variance, then means which means the more weights on my prior means, right? In contrast, if I have the larger prior variance, that means what? The smaller weight on my prior mean and the larger weight on the OLS estimates, right? So then usually or in general researchers do not want to put a stronger prior. They wanna utilize the information in the data rather than prior information, because still people believe that they may look more objective rather than subjective. So then we go with the large prior variance. I say 9. Okay, and then let me run this. Yes, they're close. Okay, but if we don't have enough information in the data, say we have only 20 observations, right? 20 observations, right? Yeah, it's because we have very large large variation of the independent variables. Let's say 1. But still it's quite. But you know that these order estimates are a bit better than this Bayesian estimation, right? Okay. So right. So yeah, please try. Okay, please try, and just make sure your code runs very correctly and without errors.